Welcome to today's lecture where we will delve into solving ordinary differential equations using the finite element method with MATLAB. In our previous lecture, we explored the manual process of solving ordinary differential equations with the finite element method, carefully walking through each step to understand the fundamentals. Today, we will build on that foundation by introducing modification to our manual approach, making it more compatible with the MATLAB implementation. These changes will streamline the process, allowing you to leverage MATLAB's powerful computational capabilities to solve ODE more efficiently. By the end of this lecture, you will have a clear understanding of how to transition from manual finite element method solution to a MATLAB based one, empowering you with the practical skill for computational problem solving in engineering and applied sciences. Here we have the example minus d to u upon dx square is equal to fx, where fx will be equal to 1 on this interval 0 to 1. With the boundary condition we have is u0 is equal to 0 and u1 is equal to 1. To solve this boundary value problem, we are using finite element method. In the very first part, we will use manual approach and then after we will use MATLAB. So here we make some changes according to the previous lecture. Okay, this step will help us to implement in the MATLAB step by step. So every step will match with the MATLAB implementation. First step is to discretize the domain, which is 0 to 1 into two equal element with 3 nodes. So here we are given the interval is 0 to 1 and this is the point 0.5. So this is first node, this is second node, this is third node. So 0, 1 and 2, these are the index of these 3 nodes, and the element between x0 to x1 we have is, say it is e1, and the element between x1 to x2 we have is e2. So these are the small part of the entire interval or the sub interval. Okay, the length of each we have is h, and this is also h, where h is equal to we have is 0.5. So these are the linear element e1 and e2 with the 3 nodes, x node, x1 and x2. For the linear element, the local stiffness matrix we have is Ke for element A between I and J, which is given as Ke is equal to 1 upon h, 1, minus 1, minus 1 and 1. H is the length of the element where we have chosen 0.5. Okay, so whenever we have any local stiffness, we always use this matrix. Ke is equal to 1 upon h, 1, minus 1, minus 1 and 1. The global stiffness matrix K is obtained by assembling the local stiff matrices, and we will have 3 by 3 matrix since there are 3 nodes. Keep in mind the order of the global stiff matrix always depend upon the number of nodes. As you can see here, the nodes are 3. That's why global stiff matrix is of order 3 by 3. Now we need to compute here the element 1 between 0 and 1. So K1 will be equal to 1 upon 0.5, 1, minus 1, minus 1 and 1. This will be equal to 2, minus 2, minus 2 and 2. Now element 2 between 1 and 2 will be K2 is equal to 1 upon 0.5. 0.5 is the value of h, and 1 minus 1 minus 1 1, which is also will be equal to 2 minus 2 minus 2 and 2. So these are the element 1 and element 2, which will help us to find out the global stiff matrix K. To initialize the global stiff matrix with the zeros, now we need to assemble the global stiff matrix, and to initialize the global stiff matrix we have to choose K is equal to 0 0 0 of a 3 by 3 order matrix, and the contribution from each element will be added to this one. So here we need to discuss how we can establish the, or how we can assemble global stiff matrix. See here, for the first element we have K00, K01, K10, K11 is equal to, we have is 2 minus 2, minus 2 and 2. This is K1. Okay, and our required global stiff matrix will be of this order, as you can see, and corresponding to this element we are here also. The element will be K00, K01, K02 in the first row, K10, K11, K12, K20, K21, K22. So these elements are here, and keep in mind this matrix, this submatrix is K1, and this submatrix is we have is K2. So when we will update this element in this matrix, we have is 2, minus 2, 0, minus 2, 2, 0, 0, 0 and 0. So when we will update in this matrix, this will be 3 by 3 order, and this is we have K1. Okay, and also you need to note that this value will appear in K1 as well as K2. Okay, similarly this is the K2 element, and the elements we have is 2, minus 2, minus 2 and 2, and when we will update this matrix in K, we have 2, minus 2, 0, minus 2, 4 and minus 2, 0, minus 2 and 2. Okay, simply if you can write it as K is equal to K1 plus K2. The K1 element we have is 2, minus 2, minus 2 and 2. But K is 3 by 3 order 0 matrix. So this element will be 0, 0. But the K2 matrix we have this element, and K11, K12, K21, K22. That's why this will be 0, 0, 0. Then we have 0, 2 and minus 2. Here will be 0, minus 2 and 2. When we will add these two matrices, we will get this answer. So in this way we can easily update for global stiffness, but this is the first local element and this is the second local stiffness, and by combining in this way we can easily establish the global stiffness matrix. And hence this is the final global stiff matrix. K is equal to 2, minus 2, 0, minus 2, 4, minus 2, 0, minus 2 and 2. To compute the load vector F for the problem, we start with the shape function for linear element and integrate over each element. Shape function are defined as the linear element between node xi and xj. The shape function are nix is equal to xj minus x upon xj minus xi, and njx is equal to x minus xi upon xj minus xi. The element load vector Fa for the element A is given by Fa is equal to, we have to integrate over xi to xj, nix and jx into fx dx, but fx we have is equal to 1, so this will reduce in this form. Fa is equal to xi xj nix and jx into 1 dx. Now by using this element load vector, we need to find out the values corresponding to these three nodes. Now uniform element length h is equal to, we have is 0.5. The first shape function n0x will be equal to 0.5 minus x upon 0.5, and after simplifying we will have 1 minus 2x, and n1x will be equal to x upon 0.5, which is 2x. Integrate each shape function. First we have to integrate from 0 to 0.5. we have is n0x. The value of n0x we have is 1 minus 2x, and integrate and simplify we get this value 0.25. Similarly we can get the value for 0 to 0.5 for n1x. Okay, and n1 is we have 2x. Integrate and simplify. After simplifying we will have 0.25. 0.25. So the element load vector for the first element we have is F1 is equal to 0.25, 0.25. So this is for the first element from 0 to 0.5. Similarly, we will compute the shape function for x1 is equal to 0.5 and x2 is equal to 1. In other words, 0.5 less than and equal to x less than and equal to 1. Okay, so n1 will be equal to, for corresponding to these two, we have is 1 minus x upon 0.5, which will be equal to 2, 1 minus x, and n2 will be equal to x minus 0.5 upon 0.5, which is 2 into x minus 0.5. Now integrate each shape function, and first we have is 0.5 to 1 and 1x. Put the value of n1x, which is 2 minus 2x, and after simplifying we will get 0.25. And that of for n2, put the value at this place, which is 2 into x minus 0.5. Integrate and simplify, which is very quite simple. We have is 0.25 after simplification. The load vector of second element we have is 0.25 and 0.25. We denote it by F2, and F1 is first element and F2 is load vector for second element. Assemble the global load vector F by summing contribution from all elements. So we have is 0.25. So we will do in this way. First we have is 0.25, 0.250, and then we have 0, 0.25 and 0.25. When we will add these two, we have this matrix. So this is the global load vector. F is equal to 0.25, 0.5, 0.25. So the global load vector we have is F equal to this matrix. Assemble the solution. The solution is given by the system of the equation, which is Ku is equal to F. Put the value of global stiff matrix, which is 2, minus 2, 0, minus 2, 4, minus 2, 0, minus 2, and 2. Here this is the U matrix. The element are U0, U1, and U2. U0, U1, and U2 are unknown values. This is the load vector, which is 0.25, 0.5, 0.25. In the above, we need to apply the boundary conditions. The boundary conditions we are given here is U0 is equal to 0, U1 is equal to 0, which implies U0 is 0 and U2 is 0. Okay, so this will reduce our system to for solving U1 only. So K reduced will be equal to 4 and F reduced we will have is only 0.5. Come back here for the more understanding. So when you will apply the boundary condition here, this value is 0 and this value is 0. Okay, so corresponding to these two elements, we have this element and this element will be 0, and also the first row and the last row, and all these boundary values will be 0. So ultimately we have is 4 U1 is equal to 0.5. So after solving the system, we will have 4 U1 is equal to 0.5, implies U1 is equal to 0.5 upon 4, which is 0.125. Now here we need to construct the full solution. Incorporate the boundary conditions. U0 is equal to 0 and U2 is equal to 0. U we have is this value 0, 1, 0.125 and 0. The piecewise linear solution Ux can be constructed as follows. For U less than and equal to x less than and equal to 0.5, Ux will be equal to U0 and 0x plus U1 and 1x is equal to, put the value of U0 and 0x, U1 and 1x, and we will have 0 into 1 minus 2x plus 0.125 into 2x, which will be equal to 0.25x. And for 0.5 less than and equal to x less than and equal to 1, Ux will be equal to U1 and 1x plus U2 and 2x is equal to 0.125 into 2 minus 2x plus the value of U2 is 0 and that of and 2 we have is 2x minus 1. After simplifying, we have 0.251 minus x. So combining these two, the full solution is ux is equal to 0.25x for 0 less than or equal to x less than or equal to 0.5, and 0.25 into 1 minus x for 0.5 less than and equal to x less than or equal to 1. The nodal values u0 is equal to 0, u0.5 is equal to 1.25, u1 is equal to 0, providing the approximate solution to the differential equation. Here we are going to apply the MATLAB, and for the same problem, minus d2u upon dx square is equal to fx for the interval 0 to 1. With the boundary condition we have is u0 is equal to 0, u1 is equal to 0, and fx is equal to 1. So these are the steps which are involved in our manual computation, and the same are in the MATLAB. Okay, so this is the MATLAB implementation. The entire code has been written carefully, and all the steps which we do manually are matched with this MATLAB code. Okay, so n is equal to, these are the number of the element. We choose in manual 2 element. Here is also the 2 element has been chosen. The length of we have is 1, and h is equal to, we have L upon n. This will the element size or the length of the element. Okay, x is equal to, we need the node coordinates that will be given by line space 0 to L, and n plus 1 points will be generated, or the node coordinates. Okay, this is the exact solution. By using the analytical approach, we have this solution, which is 1 by 2 into x into 1 minus x. Okay, so we here what we do, we will compare our approximate solution with the exact solution. That's why we need here the exact solution also. Okay, now we need to initialize matrix and vectors. K will be equal to zeros, n plus 1, n plus 1, n is equal to, we have is 2. So here the matrix will be generated 3 by 3 order, n plus 1 and n plus 1 will be 3 by 3 order matrix. This is the global stiffness matrix, and F is equal to, we have is 3 by 1 global force vector or load vector. Okay, now we need to assemble the process, and to assemble the process we need local stiffness, which is defined here. K is equal to 1 minus 1, these are the first row element, and minus 1 1, these are the second row element, and divide by h. And load vector or element force vector we have is F equal to 1 1 and product h by 2. So when you will put the value of h by 2 here, this will give us the F equal to 0.25. Now we need to assemble the global matrix. So when we have I is equal to 1, so these values which are computed here will be updated at this place, and we will have the matrix A. Okay, and will be equal to this one. So here we are using the for loop. All the values will be computed and added automatically, okay, according to the order of the matrix. So here similarly we will have the code. You can see this statement, fi I plus 1 is equal to fi I plus 1 f. So this f will be returned from this place. Okay, and the load vector will be updated by using this statement. So this is the for loop which will update both the matrix according to our node. Okay, after that we need to apply the boundary conditions, and u0 is equal to 0, u1 is equal to 0. How we will apply the boundary conditions in the above computed value? So here what you will do, k will be equal to k 2 colon 2 minus 1 and 2 and minus 1. Okay, so what we will do, this will remove first and last rows and column. Okay, left row, left column, right column, top row and bottom row, these will be removed by using this statement. And if you are using f is equal to 2 colon and minus 1, this will remove the first and last entries of a load vector. Now we need to solve this system. U will be equal to k backslash f. This will return the value of u. Now add the boundary conditions to the solution vector. So u will be equal to this is the u naught. This is u1. Okay, this u will be stored here, and this is the 0. Again u2. So these are the boundary values. These are the boundary values which are added, and this is our solution without the boundary values. Okay, so now we need to compute also the exact solution for the comparison, and just we need to pass the value, pass the x vector. Okay, so this will save the exact values. Now here we need to plot, and for the plot the numerical and exact solution, we have the statement which is plot xu. Blue color is used here with the marker. Display name is FEM solution, and this is the exact solution. X comma u exact value, red color. Display name is exact solution. Legend show and title, x label, y label are also used. Grid also on. Also we make here error analysis. So error will be equal to the analytical solution or the exact value minus approximate value, or u minus exact values. Okay, and then after we have the norm of the error. Okay, L2 error, that is square root sum of error square into h, and this will display the result by using this statement. F print function is used to display the norm of error. So now we will execute this sequence statement. You can see the blue color which are appeared in the circle are approximate solution using finite element method, and in the red color we have the exact solution. Also one more thing you need to check in the workspace. Here you can see this is the k values, 2, minus 2, minus 2 and 2. L is this one, error is 0, and see here this is the u value which are 0, 0.1250, and here is the exact values. These are also 0, 0.1250, and these two are equal. This is the x vector which is 0, 0.5001. Okay, you can see now. So all the things you can compare, these are the values 0.250 and 0.250. These are the f vectors. So all the things which we compute are available in the workspace also. What we do if we choose here n is equal to 10, we have is n is equal to 10, and again execute the code, and you can see that this is the graph. Okay, in the red color we have the exact solution, and in the circle we have the approximate solution. Okay, again we are choosing more step. I am choosing here 2, 5. So as much we have the large number of point, we have more smooth curve. Okay, you can see this is more smooth curve now, and you can easily compare the exact solution and the approximate solution using finite element method. And the errors, you can see that norm error is 0. You can see the norm error is 0. As we can update these values up to 100 and up to your desire. Okay, if I choose here n is equal to 100 and execute the code, and you can see we have more smooth curve, and both are similar solution. Okay, and error between these two we have is 0, so that both are exactly matched with each other, and error you can see here is 0. So this is the, in conclusion, we have successfully transitioned from a manual approach to solving ordinary differential equations using the finite element method to more efficient computational approach with MATLAB. This progression not only underscore the versatility and power of FEM, but also highlight the practical utility of MATLAB in handling complex calculations. Throughout this lecture, we reviewed the fundamental concept of a finite element method, introduced key modification to simplify MATLAB implementation, demonstrated the process of coding and solving ODE using MATLAB. These skills are crucial and tackling real-world engineering and scientific problems where computational method play a vital role. By integrating finite element method with MATLAB, you are now better equipped to solve a wide range of differential equations with precision and efficiency. Thank you for your attention and participation in today's lecture. I hope you found it informative and enriching. If you have any question or need further clarification, feel free to reach out. Thank you very much to see this lecture till the end.